Hello, this is a quick demo to verify that you can use the Vivado software to download the design into the Basis 3 board. Since we're going to be using the Basis 3 board in this demo, go ahead and connect it to your PC via this USB connector here labeled as 13. You will also want to ensure that this jumper is in the position shown, the jumper labeled as 16. Put in the position shown here, which is the bottom two pins. This will enable the board to be powered from the USB connector. Also, this jumper right here labeled as 10, ensure that the jumper is across the middle two pins. There are 4 pins and it must be across the middle 2 pins. That will put the board into JTAG mode. You can then turn on power by flipping the power switch labeled as 15. You may see some activity on the 7-segment display from a design already programmed into the non-volatile memory in the board. We'll be programming a new design into your board as part of this demo. Download the lab1.zip archive and unpack it into a directory near the top of your C drive. I would suggest something like ECE 4743/something. When you unpack it, you'll see that it has a couple of Verilog files in it. One called lab1.v, that'll be our design file. Another one called tb_lab1. The TB stands for test bench, and it's going to be what we're going to use to simulate this design. All of our designs that you will get in this course will have a test bench associated with them. We'll also have a Vivado project file. This one is called empty_template.xpr. This template is empty. We'll modify it to include the rest of the files in this directory. It will finally have a constraints file called basis3_master. We'll discuss what's the contents of this file in a minute. First thing you need to do is copy the empty template. So I'll do that. And then rename it to lab1.xpr. At this point, you should be able to right-click and open this empty project in Xilinx Vivado. So now our project is open. We then want to go ahead and add files to our project. We have no design sources, no constraints, and no simulation sources, so let's add those files. So I'm going to go left click on design sources, right click, do an add sources, and I'll choose add or create design sources, say next, use the plus green button, say add a file, and I will navigate to that file, which I happen to already be there. So I'm going to click on lab1, say OK. At this point, I will also want to make sure that this check mark here, copy sources in the project, is checked. If it was living in another directory, it would copy it to the local directory. I'm going to go ahead and say finish, and it will show up now under design sources. I'm going to do the same thing for the constraints. So I'll do click on constraints, add sources, add or create constraints, next, plus sign, add files. And I'm going to select the basis3_master, say OK, finish, and now this will show up under constraints. And finally, I want to add the simulation file. So I'll left click on simulation sources, add sources, add or create simulation sources, next, green plus sign, add a file, and I'll add the test bench tb_lab1 to this project. And at this point, I'm actually finished with adding all the files to this project. Let's open these files and take a quick look at what they contain. We'll first open the lab1.v file. This is our Verilog design file. It's what's going to be transformed into gates. This is as simple a Verilog file as you can have. It has an 8-bit output called LED, an 8-bit input called SW. It stands for switches. And all this assign statement does right here is it says I'm going to assign the switch inputs to the LED outputs. Well, what this will generate from a hardware viewpoint is going to connect the switch input pins to the LED output pins. So what will happen is that on the board, once I program it with this design, on the board what will happen is that I will be able to flip this switch right here, and this LED will come on. This rightmost switch is switch 0, the next one is switch 1, and so forth. I've only used the first 8 switches, so only the first 8 switches will turn on the LEDs. Let's take a look at the simulation file, TB_LEDs. This is a Verilog file, but unlike the previous file, it will not be turned into gate. Its only existence is used to test the design. And we'll take more detailed look at this, but in general, what this thing is going to do, it's simply going to apply the number 0 to 255 to the switch inputs at once every 50 nanoseconds. It will also check to see if the LED outputs do not equal the switch inputs, and if it doesn't, then it will increment an error count. When all of these test vectors have been applied, if error is 0, then it's going to display a message, all test vectors have passed, else it will display a message, some number of errors have occurred. I will always supply you a test bench with every design that we have to do so we can determine if your design implements the specifications correctly. Finally, let's look at the constraints file. This file places constraints on how the implementation is mapped to the FPGA that's on the Basis 3 board. At a minimum, what it has to do, it has to specify the mapping of our ports to pins. So here it's saying that switch 0 is mapping to package pin V17 on the FPGA device. We'll talk more about other constraints that go in this file as the semester progresses. The left-hand side of the Vivado project plane contains commands from top to bottom that you would like to execute in the order that you do the design. For example, you would first create a project, add sources to it, you might add some intellectual property blocks, then you would simulate design, and once you're happy with design, then you would actually map the design to the FPGA. So we've already added our sources. We're not going to add any intellectual property blocks to this design. So let's go ahead and run the simulation. I'm going to click on Run Simulation and say Run Behavioral Simulation. There are some other choices here that are available after I've done synthesis and implementation, and we'll explore those later. But for right now, I'm just going to run a behavioral simulation. So I left click on that. It will compile the Verilog and launch the simulator. If there are any compile errors in the Verilog, it will report them at this time. At this point, my simulator window has popped up, so let's take a look at this. This guy right here shows the hierarchy of my design. I have a Verilog module called TB_LEDs that instantiates a unit under task called Lab 1. This guy has these signals in it, switch, LED, some other internal things. If I click on this, it will show me the internal signals there. I'm going to go ahead and push that over there so I have more room for my waveforms. Here's automatically added waveforms to my simulation. It's added my inputs, which are switches, and my outputs, which are LEDs. I need to run this simulation for a period of time in order to apply test vectors to it. So I'm going to go ahead and run this for 1 microsecond. When I do that, it's applied some vectors, but I really can't see what's going on here. I'm going to need to zoom out. So let's click on here and zoom out. So I'm going to zoom out, see what's going on, and I see different vectors appearing here. This binary is sort of hard to read. So what I'm going to do is I'm going to change the radix of these two things to hex. So let's do that. So I'm going to select these and then do a right click, and here I'm going to choose radix, hexadecimal. Now I'll see hexadecimal, and as I look at these vectors being applied, I'll see that the switch inputs are counting up as expected, 0, 1, 2, 3, 4, and that the LED outputs are simply echoing that. So here I haven't applied all the vectors yet, so now at this point I will go ahead and say run 10 microseconds. That still hasn't applied all the vectors. If I go out here, I'm trying to reach 255. I'm almost there. So I'll run about 3 more microseconds. And at this point, I get the message, all test vectors have passed. So I have run all the test vectors in my design, and I have no errors. At this point, I'm going to go ahead and shut down the simulator. So I'll click X here. And when I do that, it's going to ask me if I want to save my configuration waveform file. I've made some changes to it. I've changed the radix of this to hex, and yeah, sure, I want to do that because the next time I pop up the simulator, I don't want to do that again. So I'm going to say save. I'm going to give it a name. It actually gives it a pretty good name here, TB underscore LEDs underscore behavioral. So I'll just do that and do a save. It says, do you want to add this waveform configuration file to my project? I'll say yes. And when this comes back, we'll see that this has been added to my project underneath the simulation sources entry. So here it is right there. There's my configuration. So now when I start the simulator up again, my waveforms will already be in hex format. So at this point, now that we've simulated our design, we can now transform this to gates that will then be mapped to our FPGA. The run synthesis command will synthesize this Verilog file, lab1.v, to gates that can be mapped to the FPGA. Whenever we do our designs, future designs, I'm going to ask you that before you run simulation, that you go ahead and make sure that you can run synthesis and pass it with no errors before running simulation, because you can have something pass behavioral simulation but not pass once it's been synthesized because of errors that you've done in your synthesized design. Because it's just a simple design, we went ahead and just synthesized it. We simulated before synthesizing. So at this point, now that it's been synthesized, we can now change this into an implementation that will actually map onto our chosen FPGA. So I'm going to go ahead and say OK here, and this is going to run the implementation process. If I take a look at this tab, Design Runs, it will show me a progress bar here. I can also look at the log here as I was doing with the synthesis and watch the progress of the synthesis via information messages here as well. So at this point, our implementation mapping is finished. So now we will want to generate the bit file that we'll be able to program the board with. This open implemented design choice would show us the resources used in the FPGA and a graphical floor plan arrangement. We'll do that in later labs. But for right now, we just want to generate the programming file. So I'm going to go ahead and say OK, and it will go ahead and begin generating the program file. Once that's finished, it will give me an option here of Open Hardware Manager. That's the next step that we're going to want to do in order to download this bit file over the cable into our board. So I'm going to open the Hardware Manager. It's going to give me some status messages here, and then we'll see this information that says no hardware target is open, and I'll have the choice here, Open Target. So let's go ahead and click on that, and I'll say Open New Target. So once the Open Hardware Target menu opens, I'll just click on Next. We're going to want to download to a board connected to our local machine, so I'll leave this on local server. I'll click Next. It will start a process that will talk to our board and look for it out there, and it finds it. It finds our board, and it finds that it has one device on the board. Before we do anything, you'll want to change this JTAG clock frequency from 15 megahertz to 30 megahertz. That's the frequency that's going to work with our particular FPGA device. Then you want to click Next. It'll give you a summary of the settings. Go ahead and click on Finish. At that point, it's going to try to contact the FPGA device. It's done that. It was able to communicate with it and connect up to it. It says that it's not programmed, so we're going to want to program it. So at this point, I'm going to go ahead and say Program Device. So I'll click on that, select our particular device. It's going to show what bit file is being downloaded into the board, so I'll say Program. And it will end up saying the device is programmed. It will also say that give you a warning about that it cannot detect a debug hub core. That's a normal warning, and you can ignore it. But at this point, what you should be able to do is you should be able to flip those switches on your board and see the LEDs light up. That way you verified that yes, this design has been downloaded to your board. So that concludes this project. We've taken a small Verilog design. We put it into a Vivado project. We simulated the design. We mapped it to the FPGA, and we downloaded it into the Basis 3 board. These are replicated all the steps that you'll be doing, commonly doing in our labs.